Hey guys, this is Mr. Sal. We're going to look at 6.8 applications using log functions. So we've enjoyed log functions so much that we're going to look at them in word problems.
Let's read this. I take that back. Let's not read this, okay? I'm just going to summarize it. They gave us that formula, which is really all we need. So if you guys were highly versed in seismology or earthquakes, this may be relevant to you. And if you are going into that, then it would probably be highly relevant. That's okay. We have that formula, and again, it's based on earthquakes. X represents the seismograph reading, and M would represent the Richter reading. So you guys have heard of the Richter scale probably, if you watch the news, and specifically in the time of an earthquake. The Richter scale would give us a reading, but there's also a seismograph reading. I've never seen one in person. I've never bothered to Google them, to look them up, what they look like. But this is how we calculate those values. So we do need the formula on that, okay, which we'll look at on the next problem. Given the formula, again, that's the magnitude by Richter of x, so it's a function, equals, that's a common log of x over 0.001. Now again, x is the seismograph reading. Compute the magnitude of an earthquake with a seismograph reading, which is x, of 30,000 millimeters. Round answers to the nearest tenth. And luckily for us, x is already in millimeters. So all I'm going to do is take that formula, but I'm replacing the x with 30,000 because that's my seismograph reading. Now remember, this is a function, so I need to replace the x for the m of x as well. So that'd be 30,000. 1, 2, 3. And I've got 30,000 on this side as well. Maybe you guys like the comma there, maybe not, whatever. Well, that's a common log. Now you could try to figure this out on your own. However, I don't recommend it. What I'm going to do is I'm just going to type this into the calculator, which will tell me the magnitude on a Richter scale based on a 30,000 millimeter reading on a seismograph. All right, my calculator gives me 7.477 and some change. This says around to the nearest tenth. So since the 4 is the tenths, I would look to the 7, which is 5 or more, and that would make that 7.5. So the reading on the Richter scale would be 7.5. Well, to me, I think the Richter scale kind of diminishes the difference between the two. So if we were to look at, I guess, or compare earthquakes, I don't know. I don't think the Richter does it as much justice. This one, unfortunately, we do have to read all of it just to make sure we've got it all, because it's not strictly informational. And I don't think any of this stuff is accurate on this one in terms of, well, they didn't give us a year, so. But I do want to say during the great San Francisco, oh, they did give us the year, so I take that back. This is not reliable information, all right? But in any case, in 1906, San Francisco earthquake had a magnitude of 8.3 on the Richter scale. At the same time in South America, there was an earthquake with a magnitude of 5.7 that caused only minor damage. How many times more intense was the San Francisco earthquake than the South American one? Well, and we'll round our answer to the nearest hundredth. So on this one, it's very common for us to get, trying to use this sparingly, but lazy. And we say, well, I'm just going to take 8.3 and divide it by 5.7, and I will feel good. Okay? But the answer won't. All right? So don't do that. And you guys knew better anyways, because magnitude for the Richter reading is based on that formula. So it's based on this. And it didn't specify this, but it probably should have. How much more intense was it in terms of seismograph reading, right? Otherwise, 8.3 divided by 5.7 would be accurate. So let's look at this one. We have the magnitude. Let's start with the San Francisco earthquake. All right, well, we know the magnitude on the Richter scale, which is the m of x. That was 8.3. So this should equal my common log of x over 0.001. All right, to solve this, because I have an x in the log, what I'm going to do is change this so we can see the base before we change it into exponential form. This is a common log, so my base is actually base 10 of that x over 0.001. All right, now what I want to do is change this into exponential form. So the base of the log is the base for the exponent, which is 10. And its exponent would be that 8.3, because that equals the log. And this would equal whatever it was the log of, and that was x over 0.001. All right, well, how do I solve this for x? I would multiply both sides by 0.001. And I can put that in the calculator. These 0.001s cancel, and I've got my x, which equals, that's all I can fit. But that's 199,562.2. Again, that would be millimeters. Well, we did that, and, well, that was kind of nice. However, what we also have to do is compare that with the South American earthquake. And the South American earthquake had an intensity on the Richter scale of 5.7, which would equal the common log of x over 0.001. Now, solving this is actually going to be the same exact, we're going to use the same method as we did on that last one. So I'm going to take that common log and make it a base 10, which is what it is. And from here, we'll change this into exponential form with my base 10 right there. So base 10 of my exponent, which would be 5.7. This would equal what it was the log of, which in this case is x over 0.001. Well, now to solve, we'll just multiply both sides by that 0.001 again. So those cancel, and I'm just left with my x, which my calculator gives me. So that is rounded. Now again, we did that part, and we can feel pretty good about it, but it's still not the answer. All right? It says, how many times more intense was the San Francisco earthquake than the South American one? So if I want to figure out how many more times bigger something is than another one, I would take the big thing, which in this case is 199,526.2, and I would divide it by, well, I guess the other value. So this will tell me how many times 501.2 will go into the 199,526, and my calculator gives me, sorry, it said round to the nearest hundredth, so let me take that 1 off there, and we'll make that 0.9. Don't forget to label this, though. Exponential growth has this formula. Again, I'm not worried about the reading part. What we are concerned about is this formula, which, I guess, I don't know, they didn't really define everything very well. But that P of T business right there, that would represent some kind of future value. And then whenever we see any sub-zero values like this one, not sub-zero as in below temperature, but, well, and that's not a base either. It's just telling us that's an initial value or a starting value on that. Or again, they said initial population. Now, the reason I say value for these is because we're going to be using the same formula for not population, which we will see in a moment, okay? R is the rate of growth, or the growth constant, and T is the time in years, which we do need to remember, even though I don't think for this section they give us any time in months. Otherwise, we'd have decimal values for that, okay? So in terms of population, if I wanted to figure out some kind of future value, again, it would be based on this formula, which I don't remember how they got, but someone does somewhere. And you could use this formula to figure out some kind of future value based on a rate, as long as you knew the rate, I suppose. The population of the world in 1987 was 5 billion, and the relative growth rate was estimated at 2% per year. Assuming that the world population follows an exponential growth model, which is what we just looked at, find the projected world population in 2007. Round your answer to 2 decimal places. Okay. And we're going to stick with 5 billion without all the zeros. Okay, so it's just 5 on that. Let's look at the formula, though. All right, now let's not forget, though, P of t is the future value based on the time. And P sub 0 is the initial value, which for us, in this case, is 5 billion people in 1987. So I'm going to replace just my initial population or starting population with 5 billion. Again, I'm just going to take 5 on that, just knowing that my answer will be in billions. But then they gave us a rate at 2% per year. So that is my rate. Now I'm not going to put 2 there because I need the decimal value of that, of 0.02. Now the time, well, there may be a little math on this one. It starts in 1987 and goes to 2007. And you could calculate that by just subtracting them. Some of you guys don't even need that, and that's okay either way. But in any case, you should get 20 years. So we're looking at a 20-year interval, and I'm going to replace that for my t, which is now 20. So I could type this into the calculator exactly the way that I see it. 5 times e to the power of, and again, for some of you guys in your calculators, you may need an extra set of parentheses around that exponent. Otherwise, it'll think 20 is part of a base, all right? And when I do that, I should have my answer. Again, this is P of 20 for this. All right, this says round to 2 decimal places. I've got 5.204. So it looks like I can just keep it like this, 5.20. But don't forget, that's in billions. Wait, what? All right, so I pushed a 2 in there, not 20. 20, though, gives us 7.4591234 and some change. So rounding this up would be 7.46. Again, that's in billions, though. The fox population in a certain region has a continuous growth rate of 8% per year. It is estimated that the population in the year 2010 was 29,000 foxes in that region, of course. So let's look at the formula again. I'm thinking of magnitude. Let's not do that. So this is population. The future population based on the time will equal the initial population multiplied by e to the power of the rate multiplied by the time. Now that's not A, but it should help us to get A, because we know that starting population for us, because the time is 0, part A says find a function that models the population t years after 2010. Okay, well, my initial population then would be whatever the population was in 2010, which is 29,000. And they also told us the rate was a growth rate of 8% per year. So I'm going to replace the rate with 8%. And this would be the function for finding the fox population in a certain region any number of years after 2010. Then part B, use the function from part A to estimate the fox population in the year 2016. Your answer is, the answer must be an integer. Okay, we'll just make it some full or whole value on this one. So in this formula, so there's my formula, but I'm going to replace my t values with, it's not 2016, right? Because it said t was 0 in 2010. So 2016 would be 6 years after that. So I'm going to replace my t's with 6's. So this one turns out pretty nice because I can plug that directly into my calculator. 29,000 times e to the power of 0.08 times 6. But again, don't forget you may need parentheses depending on your calculator for that exponent. The decimal is 0.157 and some change. So since it's 0.1, we're going to keep that rounded to the 6. And let's label that, this would be 46,866 foxes. Or is it foxen? Again, we're not worried about the context here slightly, all right? Because if we look just at that formula, it'd be kind of hard to understand what the crap is going on, right? What we're saying here is, what it's talking about here is half-life of, I guess, mass. Because over time, it just decays, stuff decays. I guess maybe everything does, I don't really know. Specifically, in this one it says radioactive decay is given by this formula, which means that if you took, I don't know, 100 of something, let's say grams because it's easy, and it had a half-life, let's say it had a half-life of, that's not second life, by the way. It's a half-life would be, how many years do you guys want it to be? We're just making up something. If the half-life was 50 years for whatever this substance is, and we had 100 grams, then in 50 years I would expect to have how many grams? Half of that, which is 50 grams. Well, if I had 50 grams and we went another 50 years, then how many grams would I expect to have? 25. Which again is just half of the 50. So after 50 years we get 50 grams, after another 50, 25, and so forth, okay? This formula, by the way, is pretty much the same as the population one. Let's look at that. So the population based on time, and this one is also based on time, would be the initial population multiplied by e to the power of whatever the rate is multiplied by the time. Except for just now, instead of population, we're looking at mass, or percentages even sometimes. All the problems we've done previously were growth problems. But now we're looking at decay because, well, I mean, it said decay, right? The half-life of radium is the half-life of radium-226 is 1,590 years. If a sample contains 200 milligrams, how many milligrams will remain after 3,000 years? All right, well, let's look at the formula again. Again, I'm going to point it out with the population formula, though, okay? Now, on this one, it does not tell us what the rate is, which is okay. So we get to solve for the rate first, all right? Now, this is decay, and the good news is when we solve for the rate, we get to choose what the initial value is, which will then determine what the future value is. However, it really won't matter. So let's say that we're coming into this with very limited knowledge, okay? Now we're trying to solve for the rate, which means we get to choose an initial mass, which means we don't have to use 200 milligrams yet, even though we will. So you guys tell me what mass you want to start with. So we'll say that we're going to start with 10. Now notice there's no label on the formula, which is good. So you could say 10 grams, kilograms, pounds, tons, whatever. In any case, it's just 10. And this is going to be multiplied by E, oh man, to the power of my rate multiplied by the time. Now we're finding the rate, and we know the half-life on this thing, right? How many years is it? Let me use a different color. It's 1,590 years. And if this, I guess, decayed for 1,590 years, of that 10 units, how much would we expect to be left? 5. Now here's the nice thing about this, and it was kind of pointed out on that last slide just in a very nerdy way, is I want to solve for the rate, but I don't want that 10 there to be multiplied by my E. So to solve that, I would divide both sides by 10, and this is where, I don't know, scientists or math people rejoiced. What's 5 divided by 10? It's half. Well, let's do it as a fraction. What the heck? It's half, which is the half-life. Okay? So, to solve this thing finally, though, what we need to do is, well, we're solving for that rate, which is the exponent. You could try to figure that out on your own using guess and test, but we can also use logarithms. So, that base e, right, we're going to change it into a log, and that would be a base e of that 1/2, which would equal the exponent, which is the rate, multiplied by 1,590. So that's just a change of format. We didn't change any values, just the format. So let's look back on that. Exponential form, we'll do it in green. If I had exponential form, so that would be base to the power of y equals x. This would change into the log base b of x equals y, which is what I've done on that one. In fact, maybe it'd be better or more similar if we switched those. So that would be x equals b to the power of y. These two mean the same thing, and we can go between the two as much as we want. But that's how I got that stuff in orange there at the bottom, is I just used the exponential form and changed it into its logarithm form. This next step is going to change the format once again, but no values. That's a log base e, which means I can make it a natural log of that 1/2, which equals the rate multiplied by 1590. All right, well, how am I going to solve this thing? I just want the rate. So I'm going to take both sides and divide by 1590. So those are going to cancel out as a phantom 1, which gives me the rate. And I'm going to plug that into my calculator. The natural log of 1/2 divided by 1590. Oh, man. All right, this is what my calculator gives me. Negative 0.0004. Uh-oh. And this is rounded 3/6. This is not the answer, which may seem kind of daunting at this point because of all the work we've done. This is only about halfway there, right? Because we don't want the rate. It never asked us for the rate, but we needed it in order to solve this problem. What we really want to know is how many milligrams will remain after 3,000 years. So, in this one, we're going to go back to the formula, which right now, again, is written in based on population, but it's not going to matter. We don't know the future mass, I guess, on this one. The future mass, based on time anyways, is going to be, and right now it looks like we're going to start with 200 milligrams. So that would be our initial mass, 200. And this is going to be multiplied by e to the power of the rate, which is that decimal. Sorry that's so small. I ran out of space right there. And then we're going to multiply that by the time, which is, for us on this one, we're going to multiply it by 3,000 years. Oh, man. So let's plug this. But yeah, so we don't need all those decimal places. We'll just keep it at 54.07. And this was in milligrams. So don't forget to label that in milligrams. So after 3,000 years, we would expect of this 200 milligram sample of radium-226, there would be left 54.07 milligrams, which are really quite small. Now let's look at this kind of in terms of context, okay? The mass is cut in half every about, 1,500 years, let's say, right? Well, if that's the case, then after 1,500 years, we would expect that to be cut into half, which would be 100 milligrams. But then it's another 1,500 years to get to 3,000, which would be around 50 milligrams. So that's just a way to kind of estimate that we're in the right ballpark for this in terms of cutting this in half. A wooden artifact from an ancient tomb contains 35% of carbon-14 that is present in living trees. How long ago to the nearest year was the artifact made? The half-life of carbon-14 is 5,730 years, which we do need that piece of information. Well, let's look back at the formula. So there's our formula, which we're using for this decay. And again, P of t represents the future value. But once again, they have not told us the rate. Scumbags. So we get to determine, we can find the rate based on the half-life. And once again, we have to determine what our initial value is. So if you guys had carbon-14, which I don't know what it is, how much would you like? 1. 1's good. So I'm going to make that initial value 1. Do you want it to be grams, kilograms, tons, pounds, ounces? What? Yeah, it doesn't matter. Right? So in any case, whatever we start with 1 of, it's going to be multiplied by e to the power of the rate, which we don't know, multiplied by the time, which we do know. Its half-life would be 5,730 years, which means if I started with 1, whatever unit it is, its future value would be half of that, which is 1/2. Now the good news about this, and this is the nice thing about starting with 1 as an initial value, which is a wise choice, I get to make that a phantom 1, which I think it takes off a couple steps on this thing. All right, well, just like we did before on that last problem, I'm going to change this into a logarithm. So it's going to be the log base e, because that was the base of my exponent, of 1/2, equals the rate multiplied by the 5,730. And then once again, it's a log base e, which makes it really just a natural log of 1/2. So then to solve for the rate, I'll divide both sides by 5,730, which I'll put in the calculator because that becomes a phantom 1. My rate, and I've rounded that, is 1209. So negative 0.000121. That is my rate. That is the rate of decay for carbon-14. Now that we figured out the rate, we can figure out, well, I take that back. We don't need to figure out the future value because the future value is the 35%. Okay? Let's look at this in the formula. All right? Well, let's rewrite it. All right, so we're going to make that time. But we have 2 other values that we need to fill in, and we can fill them in. All right? So we're asking on this, how long ago to the nearest year was the artifact made? Now, we've already found the rate based on the half-life. But we're looking at percentages right here. Now, 35% represents, it's kind of a current value, but it's based on what would have been a future value however many years ago it was, when it was a full artifact. So that means that the future value represented in percent would be 35% at 0.35. That's all that we have of what was in the beginning. Now, if we have 35% now, and this is a good question, is what percentage of the object did we have to start with? We had originally 100%, which is 1. Now we've seen the good things about 1 being an initial value is I can make that in phantom 1. So we're going to run through this process once again. Is I have a base e on that. So I'm going to show both steps, not that everyone needs this next step. Let's change it into a log. Log base e of 0.35, or the 35%, equals the rate, negative 0.000121, multiplied by t. And then to solve this, we'll divide both sides by the rate, negative 0.000121 on both sides. I probably should have changed that into a natural log first. Let's do that now then. So I'm going to take that natural log of the 0.35, and we'll divide that by the rate. But this now will equal just 1t. Let's type that into the calculator. All right, so I had a decimal of 0.2159 and some change. So let's head around to the nearest year. We'll keep it like that. Don't forget to label it, though. That's how long ago was it? It was 8,676 years ago. And that would be our answer. All right, there's a new formula for sound. P is the power or intensity of the sound, and P sub 0 is the weakest sound that the human ear can hear. D, they should have defined this, but that would be the sound in terms of decibels. So we'll keep that in mind. This problem says one hot water pump has a noise rating of 73 decibels. A rock concert has a noise rating of 115 decibels, which kind of sounds like they're close, right? This is kind of like the seismograph and the Richter scale thing. But they're not close at all, as it turns out. And we would expect that. A hot water a hot water pump, we wouldn't expect to be too loud. Certainly not like a rock concert. So when it asks how many times bigger it is not a matter of taking 115 and dividing it by 73. That is not what we want right there, okay? What we need is it will be based on the power, or again, the intensity of the sound, which is the p-value. So let's look at this. This is kind of like the earthquake one with the San Francisco and South America one. Let's look at the water pump first. So the water pump, it has a noise rating of 73 decibels. That's D. So I'd have 73 equals 10. That's a common log right there of P over the weakest sound that the human ear can hear. So we're going to solve this formula for P, even though we do not know what the weakest sound that a human ear can hear. Now, if you know that by heart, that's okay. It's not going to matter in the end anyways. Let's look. To solve for that common log, I'm going to have to divide both sides by 10 first. So that gives me 7.3 equals my common log of P over P sub 0. Now I'm going to change that common log into a base 10, even though we didn't need to. The reason I'm showing this is because I'm now going to change it into exponential form. So that would be 10 to the power of 7.3 would equal the sound intensity divided by the smallest or weakest sound that a human ear can hear. And then finally, to solve for P, we would multiply both sides by P sub 0, and that would give us the P value. Now that's for the water pump though, right? Now, once again, we don't know what P sub 0 is. That's 7.3, by the way. So 10 to the power of 7.3 multiplied by P sub 0. All right, same formula, except now the noise rating for the rock concert is 115 decibels. So that would equal 10 multiplied by the log, common log, of, again, we don't know what the intensity is yet, divided by the smallest or weakest sound that a human ear can hear. The process is going to work the same. I need to get rid of that 10, so I just have the log, so I'll divide by 10 on both sides. 11.5 equals my common log of the intensity divided by the weakest sound a human ear can hear. And I do want to show that base 10 of the log because it is a common log, which allows me then to change this into an exponential form. 10 to the power of 11.5 equals that P over P sub 0. Again, that's just changing a logarithm into an exponential form. What I need to do now is multiply both sides, we'll use a different color, by P sub 0, which will give me P, which is the intensity. So the P would equal 10 to the power of 11.5 multiplied by P sub 0. All right, just like the earthquake one, I want to know how much bigger it is, specifically how much bigger the concert is. So I take the concert, its intensity, which is P, that's 10 to the power of 11.5 times P sub 0. And I will divide it by the water pump intensity, which is 10 to the power of 7.3 times P sub 0. Now we see here that the P sub 0 value, which is the same no matter if you're at a concert or listening for some reason to a hot water pump. So that's just the constant value which goes away. So whether you memorized it or not didn't matter. And we can ignore that garbage, which means I can plug this directly into my calculator. So I got 15,848.93. They didn't tell us where to round, so we'll just keep it like that. But the label on this one, that's how many times more intense it is.
All right, that concludes the lesson, so thanks for watching. I hope you guys liked the lesson. If you did, click the like button. And don't forget to subscribe to the channel, and then leave a comment about the lesson below. You guys have a good day.